this beautiful day. You're dealing with very beautiful things in mathematics now. A brief review. We are considering curves. Of course, when I say curves, I mean complex curves in P2C. This means the projective space of C3 and a curve, and let's call it X, in P2, see, projective space, and this will be a Riemann surface. We're looking for interesting examples. Many very important examples occur in this way. And we have seen, as I just mentioned, but it's always the case, that it's the zero set of a homogeneous polynomial of degree d. So PD is a homogeneous polynomial. Let's call it, this is, just to be a little bit cleaner, this is projective space of a vector space. It's vector space C3, and this is a homogeneous polynomial, so I will write the notation homogeneous polynomials of degree d. Degree d. Now what's the point is this, we have homogeneous coordinates, so Z1, Z2, Z3, homogeneous coordinates. So these aren't really coordinates on projective space, they're coordinates upstairs in the vector space, homogeneous coordinates. And the picture you should have in your head is that we have chosen a base point for a line, and it's the coordinates Z1, Z2, Z3, and it doesn't matter if we multiply this by 17, 17 Z1, 17 Z2, 17 Z3, doesn't matter, some number. This is another basis for this line. I call this line W. This is a situation upstairs, so we just write this homogeneous, it's just some point in that line. And the main point is that if you multiply the coordinates by a number, which correspond to taking another basis here in the line, so if you multiply by a number, it doesn't matter, well it matters, it changes the polynomial, but it doesn't change the zero set of the polynomial. So it changes the polynomial, obviously, the polynomial varies along the line, but in a trivial way. Not trivial, but in a well organized way. And that says that PD equals 0 is well defined. This equation, is well defined on projective space. Okay? And so those are the good guys, so to speak, and the main example, the first example to talk about is the homogeneous equation of degree d, say z1 to the d, z2 to the d, z3 to the d. And this example is rightfully called in this case, x is called, I call this the Fermat curve. Again, the word curve means, complex curve means a Riemann surface that is smooth because you just check Jacobian doesn't vanish to the right points of degree d. So this gives us a beautiful curve. And I analyzed this curve for you last time. It's a great deal of fun to analyze these things. The picture that I'm suggesting for analysis of these things, for analysis of the curve, and as what I'm calling a ramified cover of P1. I explained this last time. At least this is the way I like to look at these things. You take a point not in the curve, it doesn't matter which point, but I make this convenient for our discussion. And I take this point where, now all three things can't be zero because the origin is not zero. Here's the origin here, it's not in this. And so I take, so to speak, the origin in the sense that the first variable is 1 and the other one's 0, 0. And then I take a line which is a line so where z1 is equal to 0. And that's a projective line. So a typical point in this is 0, z2, z3. And you see that then this means that this line is equal to P1c. So there's just two homogeneous coordinates. So you have a point and a line. Right? And if you have a point on this thing, say here, let's take, say, some general point, z1, z2, z2, z3, to get some general point here. None, who knows what they are, but at least one of them is not 0. And then you draw the line between them, which I draw like that. And these are all linear combinations that you can get. So the general point here is what I call zeta 1 times 1, 0, 0. I think of a movement between these 2 points. I mean, this is a copy of P1, so it's a 2-sphere, but I'm still thinking of movement between these 2 points like this. Zeta 2. So that's a linear combination, but of course I'm exaggerating here. I'm thinking of zeta 1, zeta 2 being a point in P1. So really what I mean by this is zeta 1, zeta 2, z2, zeta 2, z3. Right, I take such a point. And this point moves as zeta 1, zeta 2 moves in P1, so it goes up and down this line, and that's a copy of P1. And so then you take you join any point from here to there, you get all this family of lines. So that's the way to think about projective space. Take a point, a line, and all the lines between it. That's high school geometry, which I, by the way, love very much, as you can see. Yeah. Okay, so that's the setup, and then we need to find. The goal is to find the curve. Find the curve. So x was given by the equation z1 squared plus z2 squared plus z3 squared. No, not square. That's no good. D degree d equals 0. Okay, and so the first thing you always should do is to look at a general point. So it's completely obvious that if you take a general line, a line in general position here, that it intersects this thing in D points. The intersection of a curve of degree D with a line is D points. So if I take the generic, that's the way you should always do mathematics. Start with the generic situation. The generic situation is this intersects in D points. So if it intersects one curve in D points, you can check very easily it intersects all nearby curves, lines in D points. This intersects all points in D points. So intersection in D points. So let's see what that really means. Well, I don't know. Let's just for the heck of it say that this point here, I don't know. I started with this point here. So let's say that this point is the point 0, AB. And so that means we have the curve zeta 1, zeta 2A, zeta 3, 2B. And now we put it in the equation because it has to line a curve. So to do color coding, this is the pink equation here, defining the curve. And we put it in there and see what happens. And we get zeta 1 squared plus zeta 2 squared. Why am I writing squared here? I should write D everywhere, right? D. Yeah, I put it into the equation, D everywhere. A to the D plus B to the D equals 0. Right? And now you look at it, I'm telling you how to think about mathematics, at least how I like to think. Look at bad behavior. If you're a father of children, you should look at good behavior with your children and so on. When you're doing very well, it's very nice, right? But you should always look at what the bad behavior is here. The bad behavior here, of course, is when AD plus BD equals 0, right? Otherwise, if this is non-zero, these are D points in that line, right? You can just write them down. Right? This is some number, it might as well be 1, so, or minus, let's make that number minus 1, I don't even care. So for example, if it's minus 1, it doesn't matter what the number is, equals 0, that's the thing, that equation is zeta 1 over zeta 2. Now this affine coordinate equals 0, and that's the same thing as W to the D equals 0. Those are the D roots of unity on that line. In other words, it's hard for me to draw the picture, but these points are on the circle. This is a copy of the Riemann sphere, so this is a copy of S2, and in S2 there's the equator, right? These points are on the equator, and they're the D roots of unity, right? And of course, they won't always, if that's if that's equal to 1 or minus 1. But as this coefficient changes, of course, they're different D roots of unity. But if you start at such a good point, then you have all these good points. So the only bad points, from the point of view of this picture, and now we should start using serious English language. We call this points of ramification. So the points of ramification, where you really don't have D good points, is where that's 0. So if A to the D plus B to the D is 0, that means you're on this line, because that means Z1 has to be 0. So that means Z1 equals 0, and A to the D plus B to the D equals 0. Right? That means that this whole coefficient vanishes and you only have 1 point. You only have 1 point. Suddenly you had D points here, but you only have 1 point in that curve. So that means what's going to happen here is you're going to come, here's the bad point, here's the bad point, here's the bad point. Yeah? Yeah.
Why do they collapse to the projective line and not to the point 1, 0, 0?
Well, 1, 0, 0 is not on the curve.
Well, we say that always said Z1 is 0, not Z1. Okay.
That was the key. You're absolutely right. One of the critical things here is I took a point off the curve, right? And of course, the curve's going to hit every line. But not every point's going to be in the curve. So I take a point off the curve, and okay.
Okay. Yeah.
And this is what's going to happen. So this is what's called ramified at this point. Okay. So there's the sum of the ramification set. Ramification set. That's easily computed as we see here. This is a set of points 0, A, B, such that A to the D plus B to the D equals 0. Right? So, except for the minus sign, those are just the roots of unity around the circle, and we have a bunch of them. If D is 17, then, or that's bad because I already used 17. If D is 85, then we have 85 points here. Okay, it so to speak de-ramifies here, this de-ramifies here, de-ramifies here, but then it ramifies again and so on. Okay, so you have de-ramification points where this happens. Okay, and then I made this argument. So we fill this out. I mean, we have this picture. I won't draw de-ramification. If D is big, it's hard to draw, but it looks like something like that. Okay. And then we did a calculation with Euler, topological Euler. So we use triangle. So we take appropriate triangulation of the base. Of the base, and now that means the base, so the base of this mapping, P1C, which is Z1 equal to 0, and I use the word base because I'm considering now the mapping here of this, let me draw just for fun a 3-to-1 ramified cover, I don't know, like I have here. This is just, here is X, this is just metaphorical so you can talk about it. X over the base, which is P1. So the base is P1, and so we have a map which is the projection from X, just a projection onto that, which is a holomorphic map. It's just the projection, it's just the restriction of the project. If you remove that, that's the projection of projective space minus a point onto this line. So that's a perfectly good, it's even a bundle, it's a wonderful thing. So it's a projection onto that base. This appropriate triangulation of the base gives us that the Euler topological Euler characteristic in terms of that triangulation is the same as D times the topological Euler characteristic of the base. Because if you have a triangle downstairs, you get D triangles upstairs. If you have an edge downstairs, you get D edges upstairs. But you have to make a correction, because if you have a vertex downstairs, you get far fewer, you have D, these problem points you have to subtract off. And that's the calculation that I indicated last time. So this is Euler characteristic downstairs is 2. That is this thing. Okay, that's a review of what I talked about last time. It was extremely beautiful. And several points in the last lecture, I think was shaking his head a bit, because you have to believe that this Euler number is really well defined, right? That defined independent of the triangulation, and it is. And then in one of the notes, Jasper was asking questions about he wasn't. I think you wrote it wasn't very convincing, because all of these just adding up numbers and who knows what it means. And you really need to find another definition of all of this stuff. But what one does know from Euler is that the topological Euler characteristic of a number of this is actually more often than not negative. Well, yeah, 2 minus 2 g's, and now this is a question of what, okay, fine, I mean, that's all, this is maybe okay, but the question is what g is, and the way I defined it, and this may be an objectionable thing, is the number of handles in a handle body decomposition. Of X. And I agree with all the doubts in the audience that this is not so clear that this stuff is well defined, right? I mean, you have two handle body decompositions of something with the same number of handles. I mean, what of the same thing, 2 different handle body decompositions, and it had better be the same number of handles, right? Right? Or the topological Euler characteristic should not depend on the triangulation, right? So I think this is mathematics that is very interesting, but in order to make it more acceptable and more precise, we will need other tools, and I think Riemann knew that. Let me just give you various other possibilities for defining the genus, and various things here will follow. Here's another possibility for defining the genus, which you can relate to from your manifolds class. So another possible definition. I mean, if you believe that the Euler characteristic is well defined, this could be a definition of genus, right? Another possible definition of G is this. We define, and this was related to your manifolds class, H1, the de Rham cohomology of X is the declosed one forms modulo the D exact one form. Obviously, every exact one form is closed because D squared is equal to 0. So de Rham in the 1930s understood the importance of this cohomology. If you look at this definition here, this is very analytic, right? I mean, in some sense, right? There are forms, and these are differential equation systems. But this is the same thing. This is the same thing as the singular cohomology of X. And this is an object of a subject called algebraic topology. And this is very much related, but not exactly the same as the singular homology of X. And then you can see the relation to, this is singular homology of X. It's not the same, there may, in general. There may be something called torsion. And the singular homology of X. And maybe we're coming close to something you like. This, by a theorem which is called a Rayvich theorem, is the fundamental group of X. Now you like groups, these are fancy words. The fundamental group of X modulo the commutator of X. The fundamental group. So, I'm going to explain, well, I explained this. And now I'm not going to explain things in the middle, but I'm going to explain this. Okay? So I see English squinting. How are your glasses? Oh, it's the sun. Yeah. Right. Okay? No, not yet. How's that? Better. Okay. So I'm not going to explain that. I highly recommend that you study this subject of algebraic topology. It is fundamental for any subject in mathematics, I think. And I like very much, and you can just pick up this book and read it. It's a long book, so it'll take you a long time. But it's a very good book with a lot of examples to read. I think you've looked at the book and you're shaking your head positively. It's a nice book, I think, by Alan Hatcher. He and I have the same first name, and he and I were students together, so he's a nice professor at Cornell University. So he writes beautifully, in my opinion. So, yeah, thanks, Sasha. So let me explain the last step. Okay? So just to satisfy a number of you who are not too optimistic by this, and I particularly liked Jasper's questions. He wasn't optimistic about it either. So the fundamental group pi 1 of X. So just so you have something to deal with when you're talking about this. So we look at gamma should be a closed curve. Okay? You should keep in mind some interesting curves. So, well, let's make a Riemann surface of genus 2. This interesting Riemann surface. So, for example, a closed curve which is non-trivial has an orientation. That's what I mean, a parameterized closed curve, gamma. You can see that curve is not trivial. It's not a trivial curve because you cannot collapse it to a point. If you take this curve here, you can just collapse it to a point as nothing. But this curve, there's not much you can do with it. And furthermore, if you cut, and that was Riemann's viewpoint, cut right there along that curve, you change the topology drastically, right? So that's a really, in some sense, a non-trivial curve. And now you should ask the question, what the devil is the curve? It's a reasonable question. The first answer is, if you look in any book of topology, is everything is on a topological space. So this means if you're on a topological space, it should be a continuous curve. Okay. Now, you're really worried because somebody told you that there are space-filling curves. This means there are continuous curves that fill the sphere. So it doesn't look like this. It might fill the manifold. That's horrible. Okay? That's horrible. But for these differentiable manifolds, we can approximation theorem by smooth curves. Or at least piecewise, maybe piecewise smooth curve. And let me tell you, that's important for us because Stokes' theorem is going to be useful in all of this, right? Right? And furthermore, piecewise smooth curves, compact piecewise smooth curves are not space-filling. They really look something like this. Okay, that's a theorem because they have a Jacobian. Okay, so you can approximate that and you get the same and obtain the same fundamental group. I haven't told you what the fundamental group is, but I'm going to tell you now. So it's a space of all curves, and maybe we have a base point here, so all curves through a base point. So we look at the curves through a base point, set of curves through the base point, piecewise with base point makes 0. Now, those of you who are accustomed to thinking about analysis, look at that thing and says that's a wicked infinite dimensional thing, right? It's a very big infinite dimensional thing. All the space, all the curves, all this, yeah, terrible. So what topologists do is they look at this wicked infinite dimensional thing, modulo equivalence. And then they say, I want this equivalence somehow to be, and this is dead in Église because he really, in his remarks and so on, you talk about groups, modulo, subgroups, and normal subgroups. I notice you're amused, and I like this stuff too. So what I would like to do here, in terms of the homework of Église, is I would like to write this as G modulo a normal subgroup, right? Right? That would be great. If I have a group, and then modulo a normal subgroup, I get a group, right? By the way, this is a non-trivial thing, as I tried to mention to the Emmy Noether really made a big deal out of this in her lectures in Göttingen, this is business here. So this is not so old, this mathematics, and well, I'm sure Riemann understood everything, but okay, so what is the group? So in fact, G in this case is the space of all curves. Well, I have to tell you how to add two curves. But that's a trivial matter if intuitively anyway. I mean, you take the base point and take another curve here. Well, I'll take the ideal situation. Go around here, it's oriented, parameterized, go around here, continue here and go around here, and you get another curve. Right? And of course, you want to have it from a fixed interval, so a curve maybe is from a fixed interval. So a curve is gamma from a fixed interval into x. But then you just take half the interval and go around here, and take the other half and go around here. That's how you add these things. Aha, 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 aha. Then you look at an example. You look at the plane minus 2 points. My favorite 2 points are -1. This is a complex plane. -1 and +1. I take it out. Okay, so let's look at the plane and -2 points. Well, I don't know about this. This is a curve A, and curve A. I guess I want. well, let's make this the curve B. This is the curve A. This is the curve, let's say, I don't know, like this, curve B, it doesn't matter too much, I don't think. Curve B and so on. And then essentially you were talking to my grandson Frederick, who likes to multiply now. He's learning how to multiply. You should say, Frederick, you could multiply these things out and see what you get. You go around A, you go around B, you go backwards around A, and you go backwards around B. Right? Yeah, and Riemann was interested in this because he knew that he wanted to integrate holomorphic one forms, as you know, over this curve. This is a curve, gamma. And Riemann knew that he would integrate around A, and then he wanted to add that to the integral around B, and then he wanted to add that to the integral around minus A, and then he wanted to add that to the integral around minus B. Right? If you want to integrate, that's how you do. Isn't it true? I mean, you just add up the integrals, right? And that's stupidly zero. Right? And Riemann said, well, that's really something here. That's stupidly zero. Riemann said, I'm interested in integration, at least at this stage of the game. I want this guy to be zero, because the integral is zero. Okay? And now we're dedicating this to Église. So Église is interested in these group things, and I am too, plus me. Yeah? I'm interested in this normal sub. So the group is the curve, all the curves, and now N is generated by commutators. This guy here is called a commutator. This guy here is called a commutator. So, yeah, I want to mod out by the commutators. Yeah? And now, as everybody will tell you, if you're going to do that, it would be really good if the group generated by the commutators is a normal subgroup, so this thing is a group. And you check that N, which is now written as the commutator, it's written this way. The commutator subgroup is a normal subgroup in G. Yeah. And so we have a wonderful object to deal with. All the curves. Well, of course, we want to multiply curves together, so piecewise continuous curves, or piecewise smooth curves, because we don't want space-filling curves. Modulo the commutators. So, the Hurewicz theorem says that if you mod out this thing, the fundamental group, by the commutators, this is the Mendelian group now, equals, essentially, if you think about it right, equals all of the above. And all of the above means either the first Duhem cohomology, the singular cohomology, the singular homology. The last statement is a precise statement of Hurewicz theorem. If these things here, you have to think what it means that you have an equality. There's a little bit of a lie here. It's not much at the beginning. The beginning of life, you should lie. What?
Can you explain again how we express the integral over gamma as the integral, or as the sum of the integrals over a, b?
That is philosophy, not. No. So, no. It's not philosophy. So it's just an essential definition. So you have a piecewise smooth curve, and this is you decompose it into a decomposition of smooth curves, right? you and I both believe that the integral should be defined as the sum of the integrals over the pieces.
Yes.
Well, that's what I just did.
But why is it then the product of all those curves?
Okay.
Or do we define them to be zero?
So, first of all, you're not asking this. If I have those four curves,
yeah,
okay.
if you put them together, of course, then
then it's a closed curve.
Yeah.
The four curves together, closed curve.
Yeah.
The integral over the closed curve is the sum of the integral of the pieces.
That makes sense. Yes.
That number in this case is 0.
Mm-hmm.
Okay. Now, there's another thing. That means this closed curve. Okay.
But why?
This closed curve is not 0.
But why is it then the product of?
Oh,
of those?
I told you what the product is. If you have two, I have to tell you two things. So I have a curve, I don't know, a horrible curve that starts here and ends there.
Yeah.
Take another curve that starts here and ends here.
Mm-hmm.
Call the first one alpha and the next one beta.
Mm-hmm.
I go around alpha, do all sorts of terrible things, come back, then I go around beta. That's the product.
Oh, I thought it would be the addition of both.
Hmm?
Because you also said it would be the addition.
Well, we write it multiplicatively.
Okay,
You can
okay,
do,
so
yeah.
just the operation.
It's a question of you pay your money, take your choice with the operation. But usually we write this in terms of multiplication. So I was confusing you with the.
And why is A inverse the same as minus A?
A. What? Oh, I'm sorry. I should. Aha. Thank you very much. I should have written here minus A.
That's basically just going.
I'm sorry. I
Clockwise.
confused you by that. Yeah.
But does this mean that we go clockwise instead of counterclockwise?
Yes, that's exactly what it means.
Okay.
And that clearly, right.
Mm-hmm.
Okay? Okay? So this is just a very rough thing, but I just wanted, because a number of you were very interested in what this genus really is. The genus, oh, I haven't told you, all of the above, if you do the calculation, is the dimension of these things, these algebraic objects, you have to understand what dimension is meant, equals 2g. Actually, for those of you who want to be precise here, these things are really defined over the integers. And not, this thing is defined over the real numbers if you think, right? But this is defined and has a dimension. But these things are defined over the integers, and dimension means the rank of that thing defined over the integers. So if you have 10 copies of the integers, it's rank 10. Okay, it's called the rank of a Z module. Okay, that's it. That's some of you, I'm looking at 2 or 3 of you who listened to an algebraic topology course last year, I think. And it was, I'm sure, very valuable to, in conjunction with reading Hatcher's book. It's very nice to know. So I hope that, yes.
I'm sorry that I'm asking you.
No,
It's
it's excellent.
what is in P or Pi 1?
Pi 1.
Yeah, what's that? No.
It's called the fundamental group of X.
Oh, okay.
Oh, did I ever write it down? I never wrote it down.
It's generated by the commutators, so by all possible groups.
Oh,
Okay.
yes. Did. Yeah. Okay. I forgot to write it down. Curves modulo homotopy. Oh, I didn't even talk about homotopy, did I? No. No wonder that I made a big gap in this discussion. Thank you. Okay. So, yeah, I made a big gap here. It's no wonder you were confused. It's terrible when these things are second nature to you. You make big gaps in your brain. So it's very good that you asked me these questions. So let's go again. Curves. These are just curves. Okay. N equals the set of curves such that gamma is homotopic to 0. And that means that there is, this is the notion of homotopic. It's too bad that I messed this up, otherwise it was beautiful. So homotopic to 0, this means that you have gamma 0 equals gamma. You start out with gamma, and then you have a curve of curves, gamma t, and at the last t point you have gamma 1, which is the trivial curve. Okay? You should have stopped me sooner. Okay? So, curves, modulo curves that are trivial in some sense. They can be homotopy to 0. So, what this means is, the way you should think about this is, there's a square, and here's the interval this way, and here's the time axis this way. This is time. This is the interval. So at the beginning you have gamma equal gamma 0. This is time 0, and this is time 1. And then you have all the curves. This is gamma equals gamma time t. And if you're looking into the manifold, it means that here you have a trivial curve, say, something like this. This is gamma equals gamma 0, and then the homotopy retracts it to the trivial curve. Okay? So again, let's start. Yeah.
So does that mean if we can, I don't know, you say retract it to a trivial curve, then it's homotopic to 0?
That's right.
And
So
that's not the case for non-trivial curves.
So
like one-handed.
we're looking at the set of curves which can be retracted in this sense to the trivial curve. Maybe if you homotopy to 0, maybe I'll just write here x0. That means the trivial map to x0. Because this base point is fixed here. Okay. Now I left this step out. Right? So all curves, which is a horrible infinite dimensional thing, modulo those which are homotopic to 0, that gives you pi 1 of x. That's the fundamental group. Okay. And this, for a manifold, is a finitely generated group that's already wonderful. Okay? So pi 1 is already wonderful, but it's highly non-abelian. And that's what I wrote here. This is highly non-abelian. Yeah, so we mod out by the commutator group and we get something abelian. Hurevich says this is the same thing at all these things before. And what these things before have dimension 2g. Okay? Riemann knew this, of course. Okay? Nicholas, did that help a little bit?
At least I understand it more now.
Okay. So take the space of all curves with a base point. Show that it's a group just by adding two curves in that way. I write it multiplicatively. Okay. Now we have a natural equivalence relation, homotopy. Fortunately, this is a group equivalence relation. It works well. So we look at all the curves homotopic to 0. Yeah. It's just looking at all Cauchy sequences and then looking at all the Cauchy sequences, which is horrible infinite dimensional space. Then look at all Cauchy sequences which converge to 0 in some sense. Mod out by those. All right. We mod out by those, we get something finite dimensional, very nice. It's a finitely generated group. It's wonderful, a compact manifold. Okay, it's a finite, it's a wonderful group, but it's highly non-abelian. And what Riemann was interested in is integration, and he wants, if you have a commutator, you want the integral to be 0. So you factor out the commutator group and you get something, and what you get here actually is the first homology group. What you get here is this guy, and this guy is more or less the same as all these other guys. And this gives you a good definition of genus. And it's not debatable. It's not, I mean, it's really real mathematics, okay? And I think Euler is really real mathematics also, but it's just, not everything was proved. Right? I mean, give me a proof that the Euler number is independent of the triangulation. Right? Take two triangulations and take a common refinement of the triangulations and do the whole thing. Maybe it works. Maybe something like this works. Okay. That's enough for that. Okay. So as usual, I'm very thankful for your questions. Are there any other remarks or questions? I recommend you, yes.
What's the isomorphism? What's the isomorphism?
Where?
The first singular homology is the same as the quotient property.
Oh, if you have a curve, you have an element of, you have a singular chain,
Right.
and it has a certain kernel. I mean, that mapping is, by the way, that mapping is also for higher homology. So I mean, you have the Hurewicz isomorphisms in general. The good thing is if everything vanishes up to a certain point, then you have this theorem at that point. Okay.
And how are the higher fundamental groups defined?
Oh, the higher fundamental groups, so it's very interesting. Abik asks about the higher fundamental groups. Anybody, including somebody in the 17th century, can talk about a curve and talk about integrals over curves and so on and so on. But he's asking about the higher fundamental groups, right? Or the, yes, and so maybe you're interested in mappings of spheres, modulo homotopy, something like this, yeah? Yeah, and the amazing thing is, what Abik probably has a feeling for, I don't know, it's very non-trivial, is this is measuring something one-dimensional clearly here. But the higher homotopy groups sometimes vanish, are non-vanishing beyond dimension. And it's hard to imagine. It's a very non-trivial thing, very difficult to imagine. So, you move from pi 1 to higher, the ball game is really different. Okay? But by the way, Hatcher's a great expert at that, so you can read his papers or his work. So, okay, so I hope that gives you some indication. Okay? And I think, leave it out for now, but I will make a remark. And this remark is a picture. This is a space of all complex curves of degree D. You must be courageous in mathematics, just write some picture. The first remark is that this is a very nice thing. This is a very nice thing. This is the projective space of the homogeneous polynomials. V is now equal to C3, of course, of degree D. Because if you take a homogeneous equation, it doesn't matter if you multiply it by 100, it doesn't change the curve, right? So it's the projective space, right? And this is a very wonderful space. So this is a wonderful space of finite dimensions, and we're right here with Fermat. There's Fermat. And then we're right here over here with terrible stuff, terrible curves. I'll tell you some terrible curves that aren't so terrible. Let's look at this 3-line, well, I don't know, D lines. Oh, that wasn't general position. D lines in general position. the projective lines in general position you see, I went right through, I crossed at a triple crossing. That's not allowed for general position. General position is nothing special. So you can define general position somehow. So maybe you have D curves in general position. These are terrible, right? They're not smooth, wonderful curves, right? But here's Fermat. Fermat is this guy here. Equals 0. And now suppose there's another guy, which is another, this is another x. This is Fermat. And let's just say x is a general smooth curve. Okay? Now this is what every Italian believed and what every Italian probably if pressed could prove in the 19th century or early 20th century is, first of all, there's a smooth curve going from Fermat to x. You have to believe it, but it's really true. The terrible curves, that's a small set. It maybe is a terrible set, but maybe it deserves red, but we don't have red. But I'll make it red, almost red. So this is a terrible set. It's singular and so on, but it's small. You believe me, right? Because a good is defined by Jacobian not vanishing and things like that. That's an equation, right? So you can connect it with a smooth curve, and it says here that G is constant. Because let's call this Ft is the deformation of F around from F to because Ft is diffeomorphic to F is diffeomorphic to X. Believe me, you can prove it. Okay? Yeah.
So Ft would be a path from F to X?
Yes.
When we say that's diffeomorphic to it, I mean, in some sense we're just fixing some T?
For any T,
Okay.
so you have a smooth deformation of the manifolds,
Yeah, okay. Makes sense.
okay? And you believe that you believe it. Well, I have a smooth deformation of the equations. And that gives me a smooth deformation of the manifolds. That's what you believe and that's what you can prove. Okay? So since they're all diffeomorphic, nothing changes. And so that means that the degree formula is completely general. Yeah? That means G of X equals G minus 1, G minus 2 over 2. So that's proof of the general degree formula. And you could, I think that's a homework exercise that is a nice one that you could work out yourselves. Okay. That if you define deform the equation smoothly, which you mean by that is deforming the coefficient smoothly, and that you define that means you get a surface which moves from one curve to the other, and you have time here, and you can flow with time up on that surface from one curve to the other, and prove this theorem. Okay? So that's, yes.
So you're essentially doing this on the...
You have to talk a little louder.
So you're essentially doing this on the space of all complex curves of degree D.
That's right. And the proof goes on, you write down a manifold, which is parameterized by, if you like, projective space, P2, cross time, in the submanifold is at each time you write down the zero set of the equation, and you have the vector field on the time axis. So you're walking around the time axis. You're walking out the door, going out there to the general Riemann surface, right? And with this smooth vector field, you lift to the curves moving out the door. And you can prove that way. Okay, this is standard. That's quite elementary. Okay. Now, how many curves, how many Riemann surfaces are obtained in this way? Right? So I will lecture for 10 minutes on a very important discussion. The notion, which is invented by Riemann, of a moduli space. This notion is incredibly important in all of mathematics and applied sciences, in particular in physics. In the very rough idea, of Riemann, we look at the space of all x, such as x is a Riemann surface. You have to learn to be fearless in mathematics. Just write some huge space. Yeah. So you understand, a point in the space is a Riemann surface. I mean, a point is now a Riemann surface. And of course, you should fix some numerical invariant. The only numerical of genus G. So what we think of is we think of fixing a topological invariant. A numerical topological invariant, namely the genus. G. So Riemann had the courage to say, well, let's do that. Let's just look at that space. Now, I don't know who proved what here. Certainly not Riemann. Came later. Came later, the following remark, or maybe a theorem. I don't know who proved it. I can prove it pretty easily, but with modern tools, is that if M1 and M2 are two-dimensional orientable. This is we're considering orientable manifolds compact manifolds. Of genus G, then F1, M1, and M2 are diffeomorphic. That's very interesting. Is that not an interesting theorem? Right? That is the statement that the genus is the only invariant here of diffeomorphism. Genus is the only diffeomorphism invariant. Now, in my mind, the statement, if I would replace by homeomorphic here as topological spaces, that theorem is not difficult. But I think in order to prove diffeomorphic, it's slightly more difficult. Conceivably, they are homeomorphic, but not diffeomorphic, right? It's not so obvious. Okay? That is true, by the way, in higher dimensions. There are many examples of things that are homeomorphic manifolds, but which are not diffeomorphic. So be careful. So caveat. This is a wonderful theorem. It says Riemann space, so in Riemann's question, in the moduli question here, a fixed, a smooth structure on X. So we're looking at X, it's a diffeomorphic manifold. So really it's the question of the space, so the question of the space, so i.e. that we want to understand the space of complex structures on differentiables manifold. Now, you say, let's say compact differentiable manifold. So the first thing you take is let's call this differentiable manifold M. And we take M, let's say, to be the two-sphere. This is the first thing, let's say compact differentiable manifold. Two-sphere. Well, you work a little bit, and you find out there is only one complex structure. If you think of this correctly, let's call it X, it's complex manifold, P1C. It is the only complex structure on the two-sphere. If you want to know a little bit about the higher dimensional questions involved here, come to his talk on his thesis. Prof. This was one of the motivating things for your study of your thesis. So on higher dimensional spheres or products of spheres, things like this. There are open questions here. It's very interesting. What about the two-sphere? So what about the following question? Do we get all Riemann surfaces of genus G? So the differentiable manifold has been fixed. Surfaces of genus G. as curves in P2. Curves, call them X, in P2C. So we have this whole discussion that I've talked about for 2 lectures of all these curves. Do we get everything? That's a reasonable question, right? Do we get every possible curve? Every possible Riemann surface? So I will propose something I think you will find amusing. Riemann's count. So the dimension of the parameter space of Riemann surfaces of genus G. And this parameter space then is called by him moduli space. The numbers in this space are called moduli. Dimension of the parameter space of Riemann surfaces of genus G. Here Riemann's count is 3G minus 3. By the way, that's the complex dimension. This is the complex dimension. So if you read in Riemann, you will see 6G minus 6. This is a real dimension. And Riemann was consciously thinking over the reals and complexes. So, for example, if you have genus 10, it's a 27-dimensional complex manifold. Very interesting and very non-trivial. Interesting manifold. So, how many do we get in P2? Okay? Just for fun, how many do we get here? So, the question is where to have fun. So this is fun. You can do this while drinking cognac, but you're students, so you drink something less expensive. I haven't been drinking for about a year or so I'm saving money. Now I can drink cognac. So to have some fun, the number of curves, the dimension of this thing, well, V of course is as usual, C3, of curves of dimension D, this dimension, you combinatoric freaks of a mathematische Olympiade, here is this dimension, you know this dimension, I hope. Do you know how to compute that? I'll give you a hint. Here's my hint. Okay, that's the hint. Prabhat knows the hint, or not, yes. This is the exponent of Z1. This is A, this is B, and this is C. And this is Z1 to the A, Z2 to the B, Z3 to the C. Got it? You have to distribute D things in this monomial, right? So you have to tell yourself where you stop. You start with A, and then you stop, and then you get B, and then you stop, and so on. So that's it, okay? And so you get, at most, D plus 2 over 2 minus 3 minus 1. Well, maybe I should take out 1 here and minus 3. Okay? Here, the minus 1 is for taking out projective space. This is just the vector space, so we have to take out the projective space. Minus 3 is the dimension, not minus 3. minus 3. No, minus 8. Minus 8. Minus 8, that is the dimension of symmetries of the projector space that would take one curve into the other. This symmetry group is more or less SL3. And so you have to mod out. So you get at most this because after modding out by the symmetry, well, here you take off to get the projector space, then you mod out by the symmetry, you get this number. This is, you see, any physicist loves numbers like this. This is take these numbers and mod out and get these things. You can make this precise. Okay, you get at most that dimensional space. And you might, for fun, compare to Riemann's count. So Riemann says the space, which is correct, is dimension 3g minus 3. Put the genus formula in for g, right? So what you have to do is compare 3. What does the genus formula give you? D minus 1 over d minus 2 over 2. This is minus 3. This is Riemann's number minus this number. You get it? Right? Riemann's number minus the number of curves. And you will see you get almost nothing. You understand what I'm saying? So think about this. Nicholas is looking very mystified. So what is your question?
So what was the thing that we take out or what did we try to compute? We said we get at most how many curves, or we said we want to get
This is the number of curves modulo symmetry.
So we say we get 8 curves less?
No.
Or do you say, I mean, we said we compute the dimension
No, look, if you have this vector, z1, z, I can talk about this later, but you have this, and this is a vector v, and you have a matrix m of v, that just linear transformation of these variables takes one curve to another curve. Yeah, but that's obviously the same Riemann surface, up to by homomorphic mapping.
Okay, yeah.
So I want to mod out by symmetry.
Mm-hmm.
That's the reason I subtracted out the dimension of the symmetry group.
Mm-hmm.
Okay? That's what physicists do all the time, isn't it? They mod out by that, mod out, count dimensions. So here is the number of curves, minus 1 to make it projective, modulo symmetry to get out the symmetry. This is, you get at most this many Riemann surfaces. But Riemann says you have this many, and he's right, by the way. So, and you will see that this thing grows astronomically faster than that. And you can compute the difference, having fun to compute the difference. Riemann minus the number of curves. Pretty interesting, right? Where are these curves? All of these curves are in P3. So the ones you don't get here are in P3. Okay. Well, we'll talk about other things next time. Have a nice afternoon and evening. It's beautiful today.